Hello guys, in today's video we can talk about the list of things here you should know when you're designing a op-amp circuit. So let's get started. First one is very basic and also very important. You cannot make this, make mistake about it. So the first one is which input is positive side, which input is negative side, right? So as you can see that I already put the positive and the negative here. So but assume that we don't know. So assume so let's take a look at the circuit and try to figure out which is which. So if you have a positive voltage change on this node, let's say this one goes up, the drain of this M2 MOS should go down. Now here is the PMOS M7. So when its gate goes down, its output should goes up. So in all, when this one goes up, output goes up. That's the reason this one is the positive side of input. Of course, this one going to be negative side. Simple. Let's move forward. Second one is, what if we bias both inputs at the ground? As you can see, I use the spice and back annotate the voltage onto the pin. These two pins right now grabs them to the ground. What's gonna happen? Apparently, this guy, Q4 and Q3 gonna be off, right? And then you can see that its source is also at the ground. Why? Because when this two guys is off, no current goes through them. So that's the reason the VDS of this guy gonna be 0, right? That's the reason the source of the Q3 and the Q4 is also very, very close to ground. What about this node voltage? Well, since there's no current goes through left the branch here because this guy's off, right? So this voltage should be very, very close to the supply voltage here, which means this PMOS is also off, right? And let's look at the drain of the Q1. According to simulation, it's the same as the voltage on the left side. Right? As you can see that this is something we should pay attention to. In a simulator, everything is perfect. There's no mismatch between these two guys. There's very little leakage, so that's the reason everything is balanced. The voltage here equal to the voltage here. But in the reality, you just don't know which this Q1 device or Q4, but both of them are off, right? But you don't know which one, whose leakage is higher. So technically you have no idea about this voltage. Because this is off, this is off, this node is high Z node, high impedance node, right? It really depends on the strength of the leakage from the top and to the bottom to decide which voltage this one going to be sitting at. So in the real silicon, in some cases you're going to find out this voltage is very, very close to ground, which means this Q7 going to be on. Or in some cases, this voltage is really close to the rail here, which means this one's off. So just watch out that a lot of times simulation is right, but once in a while it could throw you off. Just remember that when a node is a high impedance node, when this side is off, this side off, its voltage is undecided. Nobody knows in reality. So now, what if we grab both nodes and then connect to the supply? What's going to happen, right? 2.5 volts here, 2.5 volts here. As you can see, according to the simulation, actually, what happened is Q3, Q4 now become a switch because gate voltage is really high, and so these two guys become a switch. If everything matched, the current through this Q5 gonna be evenly splitted distributed to the left branch, and the right branch, right? So when this one becomes a switch, half of the current goes through this branch, half of this current goes through this branch. So that's the reason this voltage is 1 VGS lower than the supply voltage. Of course, that VGS is for the PMOS. This node going to be the same as that node because this one's on 2. Now, here's the problem. So as you can see that now the source voltage is not too much lower than its drain voltage. When I say source voltage, I'm talking about Q3 and Q4, right? As you can see that there's not too much VDS here. So which means these two guys is not really in the saturation region. This is not something we want. How can you do? How can you do? Think about it. So there's a couple of ways to deal with this. One way could be that you, instead of using W equal to L equal to 1, you can really make this Q3 and Q4 weaker, which means you kind of want to increase the L over W ratio. So that means for the same amount of current, right? The current is always the same. For the same amount of current, overdrive gonna be more, which means if we keep the gate voltage the same, I'm gonna push the source lower in terms of the voltage. Therefore, you can split up the drain and source voltage here. But in reality, this is not really preferred. The reason is the minute you try to increase the L over W ratio or to decrease the WL over L ratio for the same amount of current, you lower the GM, right? As we talked about this in the other video, you want to maximize for the input stage for the sake of a offset gain, or those you kind of want to maximize its GM instead of minimizing. So how should you do, right? Kind of find a way that to make Q3 and Q4 in the saturation region. Next slides. Well, it turns out to be that another way to do it is try to manipulate its body voltage. We talked about this body effect before. So when the body voltage is lower than, for the MOS, when the body voltage is lower than the source voltage, right? We used to, in the last slides, we connect the body to the source together. But in this slide, we connect the body of this input pair to the ground. Now its source voltage is higher than its body voltage. So by doing that, the VT of Q3 and Q4 increased. So that's the reason you see that if we keep the input voltage the same, but we are able to push the source voltage lower. Now when you look at the VDS here, you got almost 0.3 volts, right? So now these two guys in saturation region, which is great. Now, we were just talking about a bit about the input range. You cannot be too low, right? Too low, the current source can be turned off. Nothing gonna work. If it goes too high, you need to leverage the body effect to push the source down a little more to give give enough VDS for this input pair. Now, what about the output voltage? When output voltage, this is relatively straightforward. So as you can see that the output voltage is this guy. Apparently cannot go as high as 2.5 volts or go as low as ground. It needs to be somewhere in between to give this Q8 some room for the VDS and give this Q7 the same thing, some room for the VDS. So the valid output range for this op-amp to work or this amplifier to work is this VL gonna be like 0.2 volts, 0.2 or 0.3 volts, or sometimes even 0.1 volts lower than the supply. And that's the maximum. Minimum gonna be this guy gonna be 0.1 to 0.3 volts higher than the ground. Alright, that's a valid reason to keep these two guys, Q8 and Q7, in the saturation region. Now, next one is the DC gain. We talked about this before in the other video. So this amplifier here actually is two-stage. The first stage is differential input stage. The gain of that, it's in terms of it's about 100 or so. The second stage is here. It's a common source stage with the input transistor is a PMOS. Right. So what we're doing here is we kind of biased up both inputs and putting an AC source across both nodes, both inputs here, and we do AC simulations. By the way, that the input AC signal is 1. We do AC simulations, and so we plot the AC signals at the node F and the out. And so by doing that, we kind of figure out the first stage gain and the second stage gain here. Here's a plot. We don't worry about the gain over frequency, but we only care about the gain at the DC. This is like 1 Hertz. It's almost a DC. So as you can see that node F, the AC voltage is about 40 dB. That means this stage here, the gain, this differential input stage, is about 40 dB. Now the blue line is the output reference to this node F. That's actually the gain of the common source, the second stage. So that's about, I would say, a little more than 35 dBs. If we add them up, that's the total gain from the input here to the output. Right, differential input to the single-ended output. The gain of that is a little more than 75, I would say 75 dBs, which is decent. Now, Opamp has a lot of gains, right? In order to make good use of those gains, we need to put the Opamp into feedback loop to make them stable. Usable. So one of the most common configuration we often use is the unit gain buffer configuration. What it does was it connected the output to the Opamp negative input. So now when this guy, let's say, has a small signal change delta, its output gonna follow, right? Because these two guys, in the ideal world, there's no voltage difference between this node, positive node, and negative node. So that's the reason we'll call it a unit gain buffer, or a source follower, not source follower, unit gain follower. In the schematic, right, we figured out at the very beginning, this is a negative node, so we connect the negative node to the output. This is a voltage source, I put it there, but the voltage source is like 0 volts, so it's equivalent to a piece of a wire. Now, what we need to do when the Opamp, when the amplifier is put in the feedback loop, one thing very important we need to check is it's a loop gain, loop response. Well, if you look at the Razavi book or some other analog design books, there are many ways to break the loops. But be careful though. When you break the loops, you're gonna make sure that the input impedance, right? In this example, we break the loop here. So when you look at this direction, the input impedance is very high, which is great, and then the output impedance is relatively low impedance when you compare with the high impedance here. So that kind of tells us that this is a great point to break the loop. Nowadays, in the Cadence or HSpice, is a specific device symbols you can use to just plug it in. You kind of plug it in anyway in the loop, and then you can do the loop analysis. But in the old days, this is the way right now I'm doing is an old timer way to break the loop. In the old days, we don't have that. So what we usually did was we used a big inductor, 1 terahenry here, to block the output signal coming to the input. And then that's the AC open, DC short, right? DC short, that's the reason does not disturb the DC bias point. AC open, it kind of isolate the output and the input here. This 1 terafarad cap. On the other side of the cap, we have an AC source here because this is a AC short, DC open, right? And also does not affect, that means when this guy is here, it does not affect the DC bias point. But when you have putting AC source here, it's gonna directly feed the AC source to this node, right? Because this is like AC short. By doing that, you kind of open up the loop, and then with the AC simulations, you're gonna figure out that what kind of loop response sound is. So ideally, because this 1 pico, we just pick up by experience, empirically, for Opamp like this, we just pick up 1 puff or a couple of puff. But by looking at the AC loop response, we're gonna tell if this 1 puff is good enough or not. The criteria is try to find out that when the loop gains 0 dB, do we still have enough phase margin? Usually, a phase margin, we're talking about 50 degrees, 60 degrees most of the time. So here's the AC loop analysis result. So let's see. 0 dB point, where's the 0 dB point? Yeah, okay, the arrow is in the wrong place. 0 dB is here. So that's the gain, the loop gain. 0 dB is here. We go down. The phase margin is about, I'll say, which is great. Actually, phase margin instead of 85, actually is a 80, I'll say, which is fantastic. So which means 1 puff is good enough for the Opamp compensation. By the way, that in most of the cases that the unit gain buffer is the worst case for loop response, because what it does was feed all the output back to the negative input, which is the worst case in terms of the AC loop gain or phase margin. So okay, here at least according to the AC analysis, looks like the compensation cap we picked is good enough. So now there's another use for the unit gain buffer structure. Is by doing that, we kind of can figure out that what is the input offset, right? If we go back a few slides, input offset is essentially the DC voltage difference between positive node and negative node when you connect the amplifier in such a configuration. So in this case, right, we see it's really not too much difference. It's about, I'll say, 40 microvolts, which is very little. But by doing that, we need to have this Q7. The multiplier of this Q7 is equal to 8. Remember in Razavi book, I was talking about, be careful about the sizing of this common source stage. Otherwise, you can just be careful about the sizing. Otherwise, you're going to end with some systematic offset. Let's take a look at the sizing, try to see if there's any problems with it. So this is the tail current. The current is, let's say, 1x. So this one's M equal to 4. So that naturally that's 4x here. 4x current at the bottom. So 1x goes up, split up to half, 0.5x for each branch. 0.5x here because M equal to 4, that's 4x on top. So for this common source stage, 4x current on top, 4x current at the bottom, no problem. There should not be any systematic offset. That's the reason you see the plus and the minus side of it, negative side of it for the inputs is so close. Now, what if we reduce the M from 8 to 4? What's going to happen? So if the minute you do that, you do the simulation again, you're going to see that the input and output, both inputs, plus side and the minus side. Now there's a 600 microvolts offset difference. We call it input offset. So what does that input offset come from? So it turns out to be that because since now, instead of using m equal to 8, we're using m equal to 4. But because the loop here, this guy's still sinking 4x of the current, 4x of the tail current here. So in order for this guy to provide the same amount of current to keep this node somewhere in the middle rail, right? Because the whole loop here is trying to keep this output voltage as close to this 1.25 volts as much possible. So now, in order for this device to do it, its VGS has to be increased for the PMOS, right? Has to be drive harder. So when you look at the voltage here, now is 1.89. Before, it was 1.95. So now the VGS of this PMOS is more. So for the smaller device, we can push 4x current out. Now, as we just, according to, remember that we did a DC gain of first stage, that's about the 40 dBs. So that's equivalent to 100x. Delta change here, you're going to get the 100 delta x change, 100 delta change as this node. So let's calculate the offset, systematic offset. Because this node move changed, it was 1.95 before, now becomes a 1.895. So this voltage change over 100, that's the calculated input referred offset for this system. That happens to be the same as the simulated result. Now you know that how important the sizing of this last stage, the common source stage, to avoid the systematic input offset. Now, the next one, supply noise. In chip design, most of the cases, supply is noisier than the ground. That's the reason people are very interested to know that if the op-amp output gonna be influenced by the supply noise. Ideally, output of the op-amp should be the function of differential input voltage, right? Nothing else, ideally. But in reality, when you have some signal, when you have noise on the supply line, you're gonna have gonna inject some noise into the output. So what I'm doing here is I did two simulations. In one, I inject 1 kilohertz sine wave into the DC supply. In the other case, I inject a 50 megahertz sine wave into the 2.5 volts DC supply. And then I look at the output and try to see how well behaved my output is. For the first case, 1 kilohertz one, as you can see that the output barely moving around, right? It's very little. It's always around 1.25 volts. It's very little wiggle for the 1 kilohertz noise on the VDD supply. But when the frequency of the noise goes up to 50 megahertz, you're going to see that the output change quite a bit. So many ways to improve this. Here we're using the MOS differential input stage and op-amp. We can flip the op-amp around, use the PMOS input stage since the current source is on top. Most probably we're going to get the better supply noise suppression. Output slew. So when you connect the op-amp as a unit gain buffer, in application, the Vin change, sometimes the Vin change could be quite large, instead of like tens of millivolts. In this case, we give a good jump about the 0.5 volts. And then the output gonna start slewing. So how do we know how fast the output gonna slew? So let's take a look at the circuit. Right, essentially the input jumped from 1. I would say slightly lower than 1.8 all the way to 1.3. The output is gonna follow slowly after, let's say, 0.5 microsecond, is eventually gonna reach there. Right. But how are we gonna calculate how long does it take? So what happened was when the positive input, right, have a negative jump here, this one jump before this one changed. Before this one jumped down, the voltage here is about 1.25 volts. This one is also 1.25 volts because this is a unit buffer. So now this voltage jumped down by 0.5 volts. This guy still there before the op-amp responds. So this transistor, this CMOS transistor is off. Since this guy's off, all the tail current gonna go through this half a branch, gonna mirror around, and then dump here. The current cannot go into this node. Very little current will go into this gate. Most of them gonna go through this cap. Since we know, relatively speaking, this node, the drain of the Q1, doesn't change too much when you compare with the output voltage, right? Output voltage gonna jump by how much? 0.5 volts. 0.5 volts here, very little change here. Here's the current. So we can use the C dV equal to I equation, try to figure out how long does it take for the output to eventually go there, right? So dt, that's the time duration, equal to this CC cap, right? 1 puff multiplied by 0.5 volts, because this guy is gonna jump for 0.5 volts over 1 microamps. 1 microamps is the tail current here. As we said, this guy can be off. All the tail current is gonna go through this guy, this left branch, go up and then copy around, dump here, and then go through this guy. So according to this C dV over I equation, we got a 0.5 microsecond. That's the result from the simulation 2. Great, we finally finished it. Guys, I hope you learned something today. If you have questions, any comments, please leave your comments below. And if you like the video, please give the video a like. It means a lot to us. Thank you.